lines and planes in space. First set of problems is very important. Suppose you have a point and it is negative 2, 3. Negative 2, 0, 3. This point is on a line. And the line is parallel to 2, 4, negative 2. Now, this line, this vector component, it's a line. It starts at well, it's not a line, it's a vector. It starts at that point, and it goes out a fixed distance, possibly and went the other way. It goes out a fixed distance, and now we are at this point right here is at 2, 4, negative 2. Okay. Now, if I multiplied this vector 2, 4, negative 2 by some arbitrary value, if I multiplied it by 1, well, I get back 2, 4, 2, and there's my vector. If t were 2 instead, well then the vector would be twice as long. If I multiplied it by negative 1, it would go in the opposite direction. If I multiplied it by 7.8, it would just be longer. If I multiply it by negative numbers, it might be longer, it might be shorter. In fact, if I multiply it by, if I let t be any value, all values, well then what I do get is this line. Okay. But there's only one problem. This line may not contain the point negative 2, 0, 3. In fact, according to my diagram, it does not. So what could we do? What could we do to make this work? Well, if to every point on this line, in particular the origin, if every point on this line, if we add negative 2 and we add 0, negative 2 to the x value, and 0 to the y value, and 3 to the v value, you know what? We'll get that line. And that line is clearly parallel to this. And if I scale it, it's still going to be parallel. Now, the equation of this line will be negative 2, 0, 3 plus t times 2, 4, negative 2. Actually, the vector. The point. Now let's add. Now let's put this over here. Let's look at it a little bit more closely. Negative 2. I can distribute the t, so I get negative 2, 0, 3 plus 2t, 4t, negative 2t, and then I add the components. I add the x components, I get negative 2 plus 2t, I add the y components, I get 4t, I add the z components, I get 3 minus 2t. This is your equation. That is, okay, so let's go over what I did more mechanically. All you do is you take the point and you add on t times this point. That is, you do negative 2 plus 2t. That's the x value. So here's the parametric equations. They want the parametric equations. I take negative 2 and I add on 2t's. That's what x equals. What does y equal? 0 plus 4t's. 0 plus 4t. And z is equal to the z value of the point plus negative 2t, or just minus 2t. And of course, you don't need to write those zeros if you don't want. But I like to write it because when I look there, I should see my point. I should see my point, negative 203. You know, I didn't do that on purpose, but I don't see my 3. I don't see negative 203. So this is 3, excuse me. And when I look at what t is being multiplied by, 2 for negative 2, it should be this. It should be that. Okay. This here, these 3 equations are called the parametric equations. Now we also want to write the symmetric equations. And let's see how we do that. What we do is we eliminate t. We eliminate t in all 3 equations. In this first equation, x plus 2 is equal to 2t. Divide by 2, x plus 2 equals t. The second equation, y is equal to 4t. Divide by 4, y over 4 is t. The third equation, take away 3 from both sides, equals to negative 2t. Divide both sides by negative 2. It's customary to leave the negative 2 as negative 2. Don't get rid of the negative sign. Now, since all of these equal t, the symmetric equations would be x plus 2 over 2, that's t. That equals to y over 4, which is also t, which is equal to z minus 3 divided by negative 2. There, that goes. And I also want you to find the direction numbers. The direction numbers are easy. The direction numbers. They're like the slopes. It's these numbers right here. It's these numbers that t is being multiplied by. In fact, it's these numbers over here as well. Direction numbers are 2, 4, negative 2. Direction numbers are like the slopes. Okay, they're like the slopes in 2 dimensions. Suppose you were told that you have a point 110 and the line that contains that point is parallel to x is equal to 3 plus 3t and y is equal to 5 minus 2t, and z is equal to negative 7 plus t. Now, think about it. Each point, x, y, z, each point is really 3, 5, negative 7, and then you add on 3, negative 2, 1, t. If we just talk about 3, negative 2, 1, that is 3, negative 2, 1. Maybe that goes like that. Again, it might go in the negative direction. Let's just say it goes like that. Well, it's 3, and if I multiply it by 2, I actually get this whole line. That if I multiply it by t, where t can be anything. T can change. Now, 3, 5, negative 2, for argument's sake, let's say it's there. So what happened is, since I'm adding them, say the origin gets displaced in that direction and that amount. Well, then all the points get displaced in that direction by that amount. And what you now get is this. The point I'm getting at is, if something is parallel to this, that is parallel to just this 3, negative 2, 1. We could ignore this. We can just ignore it. We can just ignore it because this vector, this line, is parallel to this line. And you should ignore it. Not only can you, you should. In fact, you can change those numbers. I can change these numbers to 1, 7, 4, which is, say, right there. And we play the same game. Say the origin goes that amount in that direction. Well, then every point goes in that direction for that amount. And now you get this vector, this line, which is parallel to this one anyways. So you get to ignore that. You get to ignore that. Now, this problem is very, very similar to the last one, where you were given a point and you were given a component vector that you were parallel to. So the parametric equation will be x is equal to 1 plus 3t. Plus 3t. And the y will be 0 plus negative 2t, or just negative 2t. And the z will be the 1 plus 1t. 1 plus 1t. And there is your parametric equations. Parametric equations. Now we also want to write the symmetric equations. So we solve each of the equations for t, and we set them equal. When you solve the first equation for t, you bring the 1 over. So x take away 1 is 3t. Divide by 3, now you have t. The second equation, if you just divide both sides by negative 2, you will have t. In the third equation, bring the z over. So now you have z minus 1 equals 1t. And here are your symmetric equations. This is symmetric equations. And the direction numbers are these numbers up here. 3, negative 2, 1. it's not a vector, they're numbers, so don't put the vector brackets around them. Okay, so suppose you're given these 2 points. Suppose you are given these 2 points. 2 points, even in space. I mean, just hold up 2 fingers and imagine a line that connects both of them. There's only one line that you can use to connect both of them. Okay, so given 2 points, we can get a line. The question is, what is the equation of the line? How do you describe the line? You can describe it by parametric equations and by symmetric equations. Now, let's just think for a moment that these are the 2 points. What I want to do is find the component vector. You subtract these values, you end up with 5 plus 2/3, which is 5 2/3. -3 minus 2/3. Why, that's -3 2/3. And -2 minus 1, that's -3. That is the component vector, which is 17/3, -11/3, -3. Now, I hate fractions. Why don't I just triple the lengths? And you'll see in a moment that doesn't matter. When I triple this, I just get 17. When I multiply that by 3, -11. And when I multiply that by 3, I get -9. That's like the direction vector. We go in this direction. What I want to do is add to each point something, so I end up along here. One thing I can do is, to each point, I can add on the vector. I don't know which one was which one. I can add on vector p to each point. Add on vector p to each point. Remember, if I multiply this by t, I get a lot more. I get a whole line. And since I'm multiplying by any number I wanted to, that was why I was able to multiply by 3. I multiply this vector by any value, so it becomes real long, and then I add on, say, these numbers. Or I didn't have to add on those numbers. I can add on the other point. I can add on q, which of course would be absurd only because it's more messy. The values are more messy on q. I can, to every point, I can add on that length and that direction. And I still get the same vector. So that's what I'm going to do, except I'm going to use p. So what I'm going to say is, I have this here. So I take my p, x is equal to a point. First is the point, and then the component vector part gets the t. Y is equal to the value of the point, plus, in this case minus, the vector component for y times t. And z is equal to the point, -2, minus 9t. Now you may say, oh, wait a minute. If I use these points, I would get completely different looking equations. Negative 2/3 plus 17t, x is equal to, y is equal to negative 2/3. There. Is equal to 2/3 minus 11t, and z is equal to 1 minus 9t. You'll get the same x values, but the t's won't be the same. Let me think about it. It's going to be a fraction, isn't it? Oh, I can use the last one. Here. When would the z's be equal? Is that what I want to do? Absolutely not. Okay. If t is equal to 0, the first x will be 5. When will the next x be 5? When will this be 5? When will negative 2/3 plus 17t be 5? We'll add the 2/3 to the other side. 17t will be 5 2/3, which is 17/3. T times a third is 17/3. So t would be 1/3. Okay, when t is 0, x is 0 on the left, x is 5, y is negative 3, and z is negative 2. For the right-hand side, t is a third. When t is a third, you get 17/3 minus 2/3, which is 15/3, which is 5, just like we got there. When t is a third, this is negative 11/3, plus 2/3 is negative 9/3, which is negative 3, just what we got there. When t is a third, this will be 3. 1 minus 3 is negative 2. Just what we got over here. It'll take different t values for these to match up. But these three equations plot out the same equation, the same line as these three. But don't use these three, they're messy. Just want to convince you that they're working. I don't want you to think I just make up this stuff. Nor do I want you to think it can't be understood. Okay. So, which points lie on L? Which points lie on line L? Which points lie on L? Also known as line L. And you come to know that L, the line passes through the point 2, 3, 1, negative 2, 3, 1, and is parallel to the component vector v, which is 4, 0, negative 1. And they give you some points. 2, 3, 0, 2, 1, 0, negative 6, 3, 2, and 6, 3, negative 2. I'll make one quick comment. Either both the first two lie on the line, or they both don't lie on the line, because they're opposite one another. I have to think if that's right. Okay, so we know it passes through this. Let us write down the parametric equations. It's negative 2 plus 4t. Y is equal to 3 plus 0t. That is just 3, which immediately tells me the last one is out, because y is always 3. The y value here was 1. And z is equal to 1 minus 1t, or just 1 minus t. Okay, we need to figure out if 6, 3, negative 2 is in here. Well, y is 3, that's good. I want to know what t value makes this 6, or what t value makes that negative 2. I'd rather solve the last one. 1 minus some number gives me negative 2. 1, 0, negative 1, negative 2. 3. 1 minus 3 is negative 2. So, t, if it's going to work, if this point is on the line, t has to be negative 2. Let us find the x, the y, and the z value when t is negative 2. When t is negative 2, you get 3. What happened there? I want to know when 1 minus t was negative 2. You're at 1, 0, 1, 2, 3. I want to get to negative 2. I know I did it right, but then I blew it. 0, excuse me. 1, negative 1, negative 2. So you're at 1, you take away 1, 2, 3. So that is where, oh, I see where I got 2 from, negative 2. Like I must have said, t equals 3. T is equal to 3. Sorry about the delay. T is equal to 3. I want to see if x, y, and z matches when t is 3. Well, 1 minus 3 is negative 2, which is correct. And when t is 3, y is always 3. So that match. It's this top one. X is equal to negative 2 plus 4 times 3. 4 times 3 is 12. Negative 2 plus 12 is 10. That's not 10. So no, it did not work. It did not work. Okay, let us try the second choice. And since the y is negative 3, I'll bother to check it. So we have negative 6, 3, 2. When does this equal to 2? Well, take away 1 from both sides. You get negative t is 1. If two quantities are equal, if you change their signs, they'll still be equal. So if it's going to work, if this point's going to be on the line, then t is going to have to be negative 1. So it definitely works in the last equation. It definitely works in the last equation because by design, we made it work, but we can check again. It's 1 minus -1, which is 2, so that worked. And y is always 3. It's the top one again. X is equal to -2 plus 4 times -1. That's -4. -2 plus -4 is -6. Yep, she's a winner. It's a winner. Put your money on that one. Okay, let's check 230. Let's see if that one works. 230. So z is 0. That means t has to be 1. So t has to be 1. So the last one works. When t is 1, y is 3. Y never deviates from 3. Top one. X is equal to -2 plus 4 times 1. 4 times 1 is 4. -2 plus 4, 2. 2. Here's another winner. 2, the second and third points, they're on the line. Okay, so you need to find one t value. You need to find a t value that works for one of the points. And then see if it worked for one of the coordinates, x, y, or z. And then see if it works for all three of them. Okay, turn back. Listen to the tape 5, 6, 93 times. Whatever it takes for you to understand it. Suppose I ask you if these points are on the line that I'm about to define. I'll give you a hint. Either they are or they aren't. Are these points on the line that I'm about to define? And it tells you that the line L passes through 2, 0, -3, that point, and 4, 2, -2. So it passes through those 2 points. Passes through those 2 points. So again, what we have is we have these 2 points and we have that line. So it's not so easy just to find the equation of that line. First you have to find the equation of this line, the one that crosses through the origin. Well, subtract. 4 minus 2, 2 minus 0, -2 minus -3. And then multiply that by t. That's this vector. And then to every point, add on either this point or that point. I like ones that have zeros in it. There is your equation of the line. Add 2 plus 2t. That's the x value. And the y value is 0 plus 2t as well. And the z value is -3 plus 1t. -3 plus 1t. So there is your parametric equation for the line that crossed those 2 points that I gave you. Now my question is, on the bottom I have some points. Which one of them is on the line? I would think that I would use the y value equation because it's just 2t. Okay, let us check 4, 1, -2. If 2t had to be 1, The y is the second component. First, second, third. X, y, z. If two t's are 1, then t must be a half. So, the x value will be 2 plus 2 times a half. This is 1. 2 plus 1 is 3, not 4. Let me just convince you that the second one worked. I don't need the 0. 2 times t, 2 times a half, is 1, which is correct. But it didn't work for the x value. So this one is history. This one is gone. Okay, let's check another one. Let us try -1, -3, -4. And in theory, you can take any of the equations, 2 plus 2t, the x value, set it equal to the x value, and solve. Take away 2 from both sides, so you get 2t is -3. Divide by 2, and use t equals -3/2. Okay. But again, I think it's easier to use a y value. If you don't see that, then do what I just did. Use any of the equations. So 2t should equal -1, divide by 2, divide by 2. For this to work, t has to be -1/2. And of course it won't work, because it won't work for x. I think x had to be 3/2 or -3/2. But nonetheless, let's make believe we didn't do the x. So we found out that for the y values to match, t has to be -1/2. Okay? T has to be -1/2. Let's check the x value. You get 2 times, 2 plus 2 times -1/2. 2 times -1/2 is -1. So it's 2 plus -1, which is 1. It's not matching. This point, bye-bye. It's not on the line. Before, in 2 dimensions, this is interesting. In 2 dimensions, if it was parametric, it would still be 2. In 2 dimensions, parametrics, you only had to verify it in 2 equations. Now you have to verify it in 3 equations. And that is 1t, in case you've been wondering. Okay, let's try this one next. So for the y value, 2t must equal the y value, -2. So t is -1. So 0, -2, -4, t has to be -1. So we know the second equation works. Let's verify the first. 2 plus 2 times t, which is 2 plus -2, which is 0. And it matched like a glove, fit like a glove. Positive 2 times -1 is -2. Perfect. Looking good. Last one. -3 plus 1 times -1. -3 plus -1. That's -4. There it is. That point worked. Now we have to try the fraction one. There might be more than one point that was given that lies on the line. So now we have a half. So 2t is equal to a half. On the left side, it's very, very friendly to divide by 2. But it's not so friendly to divide the right side by 2. An alternative for dividing by 2 is to multiply by the reciprocal of 2. You need to be smooth enough to do that. So t is 1/4. Okay, and we have 5/2, 1/2, -11/2 as opposed 2 negative pi quarters. I meant to say 11 quarters. I think I said negative 11 halves. And this is when t is equal to a quarter. Okay, let's try the x value. You have 2 plus 2 times a quarter. 2 times a quarter is a half. And 2 and a half, 2 plus a half is 2 and a half, which is 5 halves. Got it? The second value, second equation works. 2 times t is a half. Got that one? Let's try the last equation. And if that works, we say, okay, we found 2 points that were on that line. Negative 3 plus 1 times a quarter. This is negative 3 plus a quarter, which is negative 2 3/4. If you owe somebody a quarter, if you owe the bank $3, if you owe the bank $3, if you owe somebody $3, and you give them a quarter, you now owe them 2 3/4, which is negative 8 plus 3, excuse me, it's negative 8 plus 3 is 11 over 4. Negative 11 over 4, which is exactly right. So it turns out the last 2 points, they were both on the line. Unfortunately, you have a lot to check. It's not like y equals mx plus b. Okay. Suppose we want to find out if these 2 lines intersect. X equals 4t plus 2, y is equal to 3, z is equal to negative t plus 1. That is one line. That's not both of them, nor is it 3 of them. 2s plus t, y is equal to 2s plus 3, and z is equal to s plus 1. There's no reason why these two, the t and the s's, have to be the same. That's why we didn't have t's on the right equation as well. We used a different letter. We used s. Now, we know that y is 3. We know y is 3. There's absolutely no way around that. Y is 3. Now, if the lines are going to intersect, they're going to have to intersect at a point where y equals 3. That is, if somebody, it might intersect at this point, because y is 3. It might intersect at that point, because y is 3. It definitely will not intersect at this point here, because y is not 3. Y must be 3. And if they intersect, they both have to have the same points. That's what intersect means. That is, this y value has to be 3. And if 2s plus 3 has to be 3, then that has to be 0. Because we all know 0 plus 3 is 3. You don't have to take away 3 from both sides. What plus 3 equals 3? 0. You know that. You don't have to take away 3 from both sides. So 2 times s must be 0. If 2 times that is 0, that must be 0. So wherever they intersect, s must be 0. That is, 2 times 0 is 0, plus 2 is 2. 2 times 0 is 3. I meant to say 0, plus 3 is 3. and 0 plus 1 is 1. If they're going to intersect, they're going to intersect where x is 2, y is 3, z is 1. Now we have to go over on the left side and see if it contains that point. I mean, I can find the t that makes x2. I can find the t that makes z1. But I want the same t to make x2 and y3 and z1. So when will the x value 4t plus 2 equal to the x value? 2. Amazingly, this has to be 0 as well. 4t means 0 plus 2 really equals 2. So 4t has to be 0. So t coincidentally is also 0. It didn't really need to be that way. So what would x, y, and z over here be? Well, x is 4 times 0, 0, plus 2 is 2. And the y value is, well, it's always 3. And the z value is negative 0, which is 0, plus 1 is 1. This point matches up with that one. They intersect at 2, 3, 1. They do. They didn't have to, but they did. They intersected. Two lines do not have to intersect. And in 3, in space, they don't even have to be parallel. I mean, this line and that line. Imagine this line is in front of the board. It's 2 inches in front, but it's parallel to the board. And this line is on the board. They won't touch, nor are they parallel. They're not in the same plane. Okay, let's do this again. But now we're going to be given the equation in different forms. Here is the equations of one line. And here is an equation for the second line. And since we had such good success when it was written in the other form, parametric form, let's get it to be that one. Let's get it to be that way. Remember, this is what t is. That x over 3 is t. If x over 3 is t, then 3t is x. X is 3t. And if that's t, if y minus 2 over negative 1 is t, then negative t equals y minus 2. Y minus 2 is negative t. Just bring the 2 over. Y is 2 minus t. And z plus 1, that equals t. Bring over the 1, and you get z as negative 1. You get z as negative 1 plus t. That is solve for x and then y and then z in terms of t. Each of those equal t. Solve for t. So that's the parametric equation for the first line. Now let's go to the second line. Now remember, the parameter in the first equation was t. There's no reason why it has to be t in the second one. But how about we let it be t anyway? X minus 1 over 4 is t. So 4t is equal to x minus 1. Add the 1 to the other side, and you get that x is equal to 1 plus 4t. Y plus 2 equals t. Bring the 2 to the other side is negative 2. the y is negative 2 plus t. Z plus 3 over negative 3 is t. Multiply, and you get z plus 3 is negative 3t. Bring this 3 over is negative 3. So you get negative 3 minus 3t. Z is equal to negative 3 minus 3t. This is the second equation, the second line. It's the equation of the second line. So let me get rid of all of this. It's the equation of the second line in parametric form. I describe the second line and the first line in parametric form, where the parameter is t. And I want to see where the x's are equal. So I'm going to set these two equal to one another. 3t equals 1 plus 4t. Bring this 3t over, that is take away 3t from both sides. The left side is 0, the right side is 1 plus t. 1 plus negative 1 is 0. So t has to be negative 1. Okay. So when t is if they're going to intersect, t has to be negative 1. When t is negative 1, the x value is 3 times negative 1 or negative 3. For the record, 4 times negative 1 is negative 3. 1 plus negative 4, excuse me. 4 times negative 1 is negative 4. 1 plus negative 4 is negative 3. For the 2 points to be the same, the x values have to be the same. Now, if x is negative 1, if t is negative 1, then there's something I think went wrong. Okay. I wasn't sure if this was 2. I wasn't sure if this equation was 2t or 2 minus t. It's 2 minus t. When I crossed the t, it looked like part of them. It became part of the minus sign. So it looked like 2t. In any case, when t is negative 1, you get 2 minus negative 1 or 3. When t is negative 1, z would be negative 2. So if they're going to intersect, there it is. X is 3, y negative 3, y is 3, z is negative 3. Let's see if it works. You get negative 2 plus negative 1, which is negative 3. Nope, the y values don't match. They do not intersect. They do not intersect. T had to be negative 1 to get the x's equal. You could have tried to get the y's equal. I could have said one of the y's equals the other y value. I set those two y values equal. I'll add t to both sides. I'll add 2 to both sides. That eliminates the t's on the left and just gives me a number. It eliminates the numbers on the right and gives me 2 t's. So t must be 2. That would make the y values equal, but it wouldn't make the x's equal. So it failed. They don't intersect. You can get whichever, you can get the x's equal for a particular t, the y's equal for a particular t, or the z's equal for a particular t. And then you can see if they work in all three, for all three, actually all 6 equations. Now, suppose you were asked this. suppose the plane passes through a given point, 2, 1, 2. It passes through a given point, and I'll give you the normal, and has a normal vector n is equal to I. You want to find the equation of the plane. Now, the normal vector is I, it's 1I, no j's, no k's. Did you ever point 2, 1, 2? There it is. Now, if I take any other point, call it x, y, z, this vector, let it end there. That vector, which is x minus 2, y minus 1, and z minus 2. Maybe I left out an important comment. This point is on the plane. It's on the same plane as 2, 1, negative 2. And now, if you have a vector and you dot it with an orthogonal vector, which normal vectors are orthogonal, you get 0. So when I dot the vector in the plane with 1, 0, 0, I want to get 0. This times 1 is just x minus 2, plus this times 0 is 0. I won't even bother writing plus 0. Plus this times 0, which is 0. There it is. That's the equation of the plane. You want to say that x is 2? Fine. X is always 2. And you really should think about why that is true. Okay, you should actually see why it's true. Well, let me draw this a little bit better. Here is your vector 1, 0, 0. So that's the x or the I direction, that's y, and that's z. Now, if you're perpendicular, you must be going this way. Because remember, may not look it, but that's the right angle right there. Perpendicular is up or down, okay? Up or down. And the x value for our particular point is 2. And if you're going straight up, that means x is equal to 2. X is always 2. X is always 2. And somewhere, well actually, you need to move over to 1. You need to move over here. Here is, let me clean up the space a little bit. If we move over 1 under y, that would be 2, 1, 0. And if we go up 2, 1, 2, eventually we'll be at 2, 1, 0. But nonetheless, it goes like this. X and down there. X is always 2. X is always 2. And it crossed not 2, 1, 0, excuse me, but 2, 1, 2. It crossed 2, 1, 2. it crosses the point 2, 1, 2. But that's where x is a constant. If you go just straight up, x is a constant. But if you dot it, you dot the correct vectors, you get the same equation, x minus 2 equals 0. We do another one like that. They tend to bother students. Okay. The plane crosses the following point. The plane crosses 3, 2, 2. Crosses 3, 2, 2. Okay. And has a normal vector equal to 2, 3, negative 1. So again, here's a point 3, 2, 2. And here's an arbitrary vector, arbitrary point. Now, actually, that point in theory can be anywhere. It can be in the plane or not. But now, this vector, that vector which is x minus 3, y minus 2, z minus 2, that vector, if I dot it with the normal vector, and I get 0. That means that this vector x, y, z had to be in the plane. In fact, if it is in the plane, then this vector right here, that's the vector in the plane. Here's a normal vector of that plane. Any vector in the plane dotted with the normal vector will give you 0. So I pick an arbitrary point and I say, if this equation right here is true, then that point is in the plane. 2 times x minus 3 plus 3 times y minus 2 plus negative 1, or negative 1 times z minus 2. This is 0. And let me clean this up a little bit. So the calculus is done. Now we just have to clean it up. This is 2x minus 6 plus 3y minus 6 minus z plus 2 equals to 0. 2x plus 3y minus z minus 6 is minus 12 plus 2 more is minus 10 equals 0. It's customary to leave the constant on the other side. 2x plus 3y minus z, bring the minus 10 to the other side as plus 10. And here is the equation of the plane. Only points that satisfy this equation, when you connect it to 3, 2, 2, you'll get a vector in the plane, and then when you dot it with the normal vector, it'll give you 0. Only x, y, and z values that satisfy this, like 2 times 5 is 10, plus 0, minus 0, that point is on the plane. Because 2 times the x value plus 3 times the y value minus the z value gives you 10. That's how you get to hang out on the line. Every point on the plane, every point on the plane has an x, y, and z value. You get to hang out on the plane, is when you double the x value and add 3 times the y value and take away the z value and get 10, you get to hang out on the plane. You get to be on the plane. Now, what if the plane contains 3 points? If you think about it, if you just draw 2 points, that doesn't give you a plane. Plane is like your wall. But imagine the wall goes in all directions forever. But that doesn't mean it take up all the space. I mean, if your wall went to the left forever and to the right forever and up forever and down forever, it won't touch you. I mean, I doubt that you're on the wall right now. Just look at the wall and imagine it went up forever and down forever, and look at one of your walls. Up forever, down forever, to the left forever, to the right forever. It doesn't really, it's not going to touch you. If you're 5 feet from the wall and the wall suddenly got taller and went lower and to the left and to the right, you're still the same distance from the wall. And just take her pencil. Take her pencil and put her sheet of, and touch a sheet of paper to it. Okay, the pencil, there's your pencil, it crosses those 2 points. But now, if you put a piece of paper to it and you rotate the pencil, so the sheet of paper is a plane. If you rotate the pencil, the plane is rotating. The plane isn't staying the same. But you know what? If you put 3 points, you take 3 points in space, and you put your paper so that it's touching the 3 points, that paper is not moving. It can't move. But on the pencil, it can rotate. And so you're not really moving the pencil. You're rotating the pencil, but it stays in the same position. Okay, 2 points does not determine or plane. 3 points do. Think about that. Okay, so I'm going to give you 3 points, and I want to find the equation of a plane. If 3 points determine a plane, then we should be able to write down the equation of the plane. Okay, so I have 3 points. One of them happens to be at the origin. I have this point, I have, say, that point, and I have that point. And don't get caught up thinking, where should it be? Should this point be down here? Should it be there? Doesn't matter. Doesn't matter. So here are 3 points. Well, if I can calculate that vector, it's very simple to do head minus tail, because that's 0. In fact, this is their vector component. 1, 2, 3. And there's another vector. Since the tail is at the origin, the other vector is just negative 2, 3, 5. So I have 2 vectors, call them u and v. Now, how might I go about finding the equation of the plane? Well, what I want to do is I want to cross u and v. I want to cross 1, 2, 3 with negative 2, 3, 5, I, j, and k. You do the spaghetti method and actually have this worked out. You get 3, 9, negative 7. The thing is, that vector is normal, perfect orthogonal to u and v. Remember, if you cross u and v, u is going to be orthogonal to that, and v is going to be orthogonal to that. In fact, I want to find out which vectors are orthogonal to this. That's the vectors I want. That's the vectors I want. This vector on this plane will be orthogonal to 3, 9, negative 7. This vector, all of them. So I take an arbitrary point, x, y, and z. As long as x, y, z, when I dot it, that's the vector, when I dot it with, so let me be a little bit more clear. This vector, if it ends at x, y, z, then the vector, since it started at origin, the vector component would be x, y, z. If I dot it with 3, 9, negative 7, I want to get 0. So it's 3x plus 9y minus 7z equals 0. That's the equation of my plane. That's the equation of my plane. Any vector that when I dot it with that perpendicular vector with u cross v, if I get 0, that vector had to be normal or perpendicular to the normal vector. That means it was in the plane. It had to be perpendicular to u cross v, which is the set of points in the plane. You can't get other points that aren't in the plane, but that are orthogonal. Okay, now, how about we have the plane contains these two lines, which was very similar to what we just did. We found two lines, two vectors. That's one equation of a line. That's an equation of one line. And here is an equation of another line. I don't like working with symmetric equations, so I write it parametrically. This is x. If x minus 1, that's t. They're all t. If this equals t, then negative 2t is equal to x minus 1. And I'll add the 1 to the other side. The x is 1 minus 2t. And if y minus 4 equals to t, add the 4 to the other side, y is 4 plus t. 4 plus t. Y is 4 plus t. The last one is easy. Z equals t. So that's the parametric equations for the first line. It describes the first line. Now the second line. This is t. Negative 3t is x minus 2. Bring the 2 to the other side. This is t. Y minus 1 over 4 is t. 4t. This product, 4t, equals y minus 1. Add the 1 to the other side, and 1 plus 4t. Now let's solve z. Let's solve for z. We know that z minus 2 over negative 1 is t. You multiply, you get negative t equals z minus 2. Bring the 2 to the other side. You get z equals 2 minus t. Z is equal to 2 take away t. I want to find a normal vector. That's my whole goal here, is to find a normal vector. So I need to find some points on each of these lines. If t is 0, then x is 1 and y is 4 and z is 0. So I found one point. If t is 1, 1 minus 2 times 1. 1 minus 2 is negative 1. 4 plus 1 is 5. And t is 1. So from there, I can get a vector. I have 1 point and another point. Do head minus tail. 1 minus negative 1 is 2. 4 minus 5 is negative 1. 0 minus 1 is negative 1. You wanted to subtract the other way? Fine, but it's not going to matter. Okay, on the right-hand side, I'll let t be the same values. If t is 0, you just get 2, 1, 2. X is 2, y is 1, z is 0. If t is 1, on the other hand, you get 2 minus 3, which is negative 1. You get 1 plus 4, which is 5. And you get 2 minus 1, which is 1. So that gave us 2 points. 2, 1, 0, negative 1, 5, 1. So we'll call it vector 2, head minus tail. Negative 1 minus 2 is negative 3. 5 minus 1 is 4. 1 minus 0 is 1. So we now have 2 vectors. Now, if you think of it, 2 lines. Okay, well, I take that back. So the plane contains these 2 lines. The planes do contain these 2 lines. So what I did was, is I found 2 vectors starting from the origin, because I did head minus tail, found 2 vectors that lie on this plane. And these 2 vectors, they're on the very bottom of the board. I found 2 vectors that lie on this plane. They gave me 2 lines on this plane, and I found 2 vectors on the plane. And I found 2 points on the first line, that gave me a vector. Found 2 points on the second line, that gave me a vector. So maybe that's V1, maybe V2 is a lot longer, that's V2. If I cross it, I'll find a perpendicular vector. Find a normal vector. V1 cross V2. V1, V2. And we find this determinant by doing the spaghetti method. And what I got was 5, 5, 5. Now, what I want, that's perpendicular. If I take any vector, now remember that the first line, line 1, it contained the points 1, 4, 0, That was when t was 0, after that mattered, and negative 1, 5, 1. And the second line, line 2, it contained 2, 1, 2, and negative 1, 5, 1. Now first of all, if you just look at these 4 points, you might see something amazing about them. If you add the x, y's, and z's, if you add the x, y's, and z's, you keep getting 5. In fact, that's going to be the equation. X, y plus z is 5. But let's suppose we don't know that. So now, I take a vector that's I pick a point on the line. Now remember, I have a few points. I have 1, 4, 0. I have negative 1, 5, 1. Oh, this point was the same. I didn't even realize that. 2, 1, 2. So we actually found a point of intersection. I have a few points. Now, what I do is, I'm going to get rid of this graph. So what I do is I pick an arbitrary point on the plane. Now, since this point is on the plane, if I compute this vector, which of course will be x minus negative 1, which is x plus 1, y minus 5, z minus 1, if I take that vector and I dot it with my normal vector, I should get 0. But you can scale this normal vector down. You can divide each value by 5. It's not going to affect the fact that it's 0. In fact, you can call it 5 times it. Okay, actually the 5 is not going to matter. You want to leave the 5, leave it. 5, 5, 5, or 1, 1, 1. You get x plus 1, y minus 5, z minus 1. I'm going to dot this with 1, 1, 1. I get this times 1, which is x plus 1, or 5 times x plus 1, plus this times 1, which is y minus 5, or this times 5, which would be 5 times y minus 5, plus z minus 1 times 1, which is z minus 1, or it's 5 times z minus 1. And I'm supposed to get 0. Well, the first thing I would do on the bottom one is I would divide by 5. I would divide by 5. 0 over 5 is 0. This is z minus 1, which I have. This is x plus 5, which I have. And this is x plus 1, which I have. You can scale it down if you're setting it equal to 0, and we are. So what I have is x plus y plus z, x plus y, plus z. 1 minus 5 is negative 4, minus 1 is negative 5, equals 0. Well, if I add 5 to both sides, I get just what I'm supposed to get. I get that x plus y plus z is 5. And that's the equation of the line. That's the equation of the line. You don't have to, you can scale down the normal vector. If two vectors are parallel, I meant to say perpendicular. If two vectors are perpendicular, like this vector, we're in R2 now, right in the blackboard. Those two vectors are perpendicular. Well, if I make, that means the dot product is 0. If this is u and this piece is v, u dot v is 0 because it's a right angle. If I make it longer, if I make v longer, call it w now. The longer one is w. U and W is still at a right angle. It's 0. If I make it longer, it's still 0. If I make U shorter, if I make it shorter, it's still a right angle. It's still 0. That is why you can scale down the normal vector. If two vectors are perpendicular, that is, they meet at a right angle, the dot product will be 0, regardless of the size, their lengths. So, I'm going to give you two planes, equation of two planes, and we want to decide if they're orthogonal or not. Are they orthogonal? Are they perpendicular? Are they parallel? Well, the normal vector to the first plane is 5, -3, and the understood 1. It's 5, -3, 1. Normal to the second vector, second plane, is our 1, 4, 7. The 1, the 4, the 7. Let's compute the dot product of the normals. N1 dotted with N2. That is 5, -3, 1, dotted with 1, 4, 7. 5 times 1 is 5. -3 times 4 is -12. 1 times 7 is 7. Plus 7. 5 plus 7 is 12. Take away 12, you get 0. Now, if you think about it, this line and this line, they meet at a right angle. Well, call this U and V. What's normal to V? Well, what's normal to V is that one. Call that N sub V, normal to V. Now, you see where U is. What's normal to U? This vector. Call it normal N sub U. Well, yeah. N sub V dot NU and NV, they meet at right angles. They're orthogonal. So, you get 0. If two vectors are orthogonal, then the normals will be orthogonal. Okay, so the two planes on the very top on the left, they are orthogonal. Think about what it means for planes to meet at right angles. I mean, just look at the corner. You have one wall, then you have the floor. They meet at right angles. They really do. Let's see if I can draw that better. So maybe this is your floor, and this is one of the walls, and well, that didn't go well. They meet at right angles. Of course, the wall goes down forever, and the floor goes across forever. The wall goes down forever, and the floor, that wasn't very straight, was it? The floor goes across forever. But nonetheless, they're perpendicular. They meet at a right angle. They meet at a right angle. That's the wall, that point is on the floor. They meet at a right angle. That's what we're asking. How about we find the angle that they meet at? What I just drew. Boom, 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 choo, choo, choo. This is one plane, this is another, and they met at right angles. But what if they don't meet at right angles? What if they didn't meet at a right angle? Suppose you have x minus 3y plus 6z is 4, and 5x plus y minus z is also 4. So let's find the normals. Let's see if they are orthogonal. First thing I'll do is, the normal is 1, negative 3, 6. It's 1, negative 3, 6. And the normal for the second one is 5, 1, negative 1. 5, 1, negative 1. And if I dot them, n1 dot n2, that's 5. That product is 5. That product is negative 3. 5 minus 3 is 2. That product is negative 6. 2 minus 6 is negative 4. It's not 0. So let's find the angle between them. Remember, the angle between them is it's just going to be n1 dot n2 divided by the length of n1 times the length of n2. Well, I just did the numerator. That was pretty good. Now I'll do the denominator. 1 squared plus 3 squared plus 6 squared. 1 squared plus 3 squared plus 6 squared times n2 lengths, the length of n2. 5 squared plus 1 squared plus 1 squared. So we get negative 4 over the square root of 46 times the square root of 27. That's what the cosine of the angle is. You want to find the angle. It's the cosine inverse of negative 4 over the square root of 46 times the square root of 27. I want to think about one thing first. It goes from 0 to 180. Good. Okay. It's more than 90. Is that cool? Yeah, that's fine. That's an exact answer. You want an approximation? Do that. I don't do approximations. Math is exact. Besides, you shouldn't have a calculator near you. Now we want to graph this. Graph their plane, whose equation is this. And the best way to do this, and here it is to find the intercepts. Let x and y be 0. Find z. Let x and z be 0. Find y. Let our z was missing, to let y and z be 0. Find x. Well, the first one, if x and y are 0, then these aren't there. You just have 6z is 12. After all, 4 times 0 is 0, plus 2 times 0 is 0, plus 6z. 0 plus 0 plus 6z is 6z. And that equals 12. That's just what I wrote. So z is 2. 6 times 2, 12. If x and z are 0, only the y term survives. Make sure to include the sign in front of it. 2y is 12. 2 times some number is 12. Ooh, I know that number. It's 6. 2 times 6 is 12. Y and z are 0. So what survived is 4 times some number, which we're calling x, is 12. 4 times 3 is 12. The x is 3. So let me write this down here. Z is 2. It crosses the y-axis at 6. It crosses the x-axis right at 3. With those 3 intercepts, I can draw my graph. In 2 dimensions, if you had the x and y intercept, you can draw the graph. For example, you can draw the line. If it crossed here and here, there it is. But in 3 dimensions, we have another dimension. That line comes out of the border. It goes into the board. A line becomes 3 dimensions. Excuse me. A line becomes a plane in the 3rd dimension. X. So x is 3 for argument's sake. We'll call that 3. Y-intercept is 6. 1, 2, 3, 4, 5, 6. The z-intercept is at 2. And basically, you should draw that. By no means am I saying it looks like a triangle. I am not saying that. That is, the plane does not look like a triangle. But if you can picture what lies on this triangle, well then just extend it. Up, down, left, right, just extend it. Make this line go out. Imagine this line going out. Imagine this line going out. So if you can understand everything inside here, if you can understand what that is, you got the, well, that didn't come out the way. If you could understand, quote, the points that lie on that triangle, triangular shape, then you have it. Just expand it out. Okay, I mean, nobody can draw a plane. The best artists in the world cannot draw a plane. The reason is, it goes out forever. It goes up forever, down forever, to the left forever. The greatest artists in the world can't do that. There's not a, it'll take forever to do. There's not enough for paint or chalk or whatever kind of writing instrument this artist is going to use. There's not enough canvas in the world to do it because it goes up forever. How are you going to have enough paper? And even if you went up forever, now you have to go down forever. That triangular region is enough to motivate what the plane looks like. And that's what's going on there. You have to motivate what it looks like. You couldn't possibly draw it. Okay. How about we have that x plus z equal to 5. That is, x can be anything. X can be anything you want. This means x can vary. It can vary. It can be anything. When we had y was equal to 15 in 2 dimensions, you go up to 15 and x could be 1, x can be 2, x can be negative 3 over 7, x can be the square root of 7, and y is still 3. You get all of these points. X was able to be anything. X was able to be anything. And if you wanted to make up a table, x, y, remember, y is 15. When x is 0, what's y? 15. When x is negative 7, what's y? 15. When x is 2.8, what's y? 15. X can be anything. Okay, so let's ignore x for a moment. Let's just pretend maybe x is 0. You have that y, well, let me not rewrite it. It's right there. Y plus z is 15. So here's the y, and here's the z, and I think I said y plus z is 15. I meant to say 5. Well, if y is 5, but z is 0, you're right there. And if z is 5, and y is 0, hit 5. In fact, you get this line. But the thing is, you can come out this way as well. Because, for example, this point is x, y is 5, z is 0, and x is 0. If I come out to here, and notice that y plus z is 0, if I come out to here, maybe x is 2. So I have x is 2, y is 0, and z is still 0. Well, y plus z is 5. And if I, no, I'm just not going parallel to x2, am I? Let me go parallel to x. Okay, this point right here is y is 0, and z is 0, and x is 0. But now I'm going in the x direction. Right here, x is 2. But when I look at y, it's still 0, and I didn't go up any yet. Z is still 0. And over here, maybe x is 7, but y is still 5, and I didn't go up any. And if we come to the other extreme, y is 5, I'm going to say z is 5, and x and y are both 0. Now, if I come across here, if I just come across, let's see how I should do this. Parallel to the z. I'm trying to go parallel to z. My marker doesn't obey me. This point right there, z is 5. Well, x is 2, y is 0, z is 5. Notice x plus y plus z is 5. Y plus z is 5. Everywhere, y plus z is 5. Even at this point right here, x is still 0. Maybe y is 3 and z is 2. But x plus 5 is 0. If I come across, it's still going to happen. Maybe here x is 1. But I didn't change x and y. It's 3 and 2. In fact, the final answer is everything on that wall. Think of that as a wall. I want to get, but let me redraw this, and then it'll be done. Y is 5, z is 5. Those are all the points where x plus y is 0, given that x is, y plus z is 5. Y plus z is 5, but x is always 0. but I can come out in the x direction. There it is. Think of this, I want you to see, this is like a board lying on the floor. No, this is on the floor and this is on the wall. This is in midair. This is in midair. And of course, it goes out this way forever. It goes down. It goes up here. It goes up here. So what I drew is not a plane. It's just part of the plane. Actually, I want to reconsider one comment I just made. No. It doesn't go out any further. Excuse me. It does not go out further. It does not go out further here. Okay? But, well, I take that back. Of course it can go out further this way because that just changes x. It can go out further this way. Can it really go out further this way? And the answer is yes. Because what's happening, to get here, y would be bigger than 5. If you know what? We're going down. Z is going to be negative. Y is going to be 7 there. And the x value, not that it matters, it's going to be whatever that is. Say negative 2. I don't want to say negative 2, negative 3. But the y value will be negative 2. The z value will be negative 2. Why? Because y plus z has to be 5. So yeah, it has to be. It's a plane. It can go in any direction, bigger and bigger. It can go in that direction, not any direction. It really can't go that way. It can't go that way. It has to expand like this. And there it is. Enough of that. So I'm going to give you two planes, the equation, of course, of two planes. And I'm going to ask you to find the points, if any, of intersection. And then I'm going to think about that. I'm going to find the lines of intersection, actually. Now, two planes can intersect in a line. Just look at the wall and the floor. And they clearly intersect in a line. If two planes intersect, they can intersect in a line. They cannot intersect. They cannot intersect. Look at the ceiling and look at the floor. I don't think they're going to intersect anywhere soon. If you expand the ceiling up and down, left and right forever, forward, backward, left, right forever, and if you expand the floor in all directions, they won't ever meet. Can two planes meet at just one point? You should think about that one. Can two planes meet at one point? Okay, so what we're going to do is we're going to try to solve this system of equations. Two equations, two unknowns. Three unknowns. That is, we'll have an open variable. That is, we'll have a parameter. If I double the second equation, then I can add it to, if I double the first equation, and now if I just add it to the second equation, what happens is the 4 y's cancel. Coincidentally, so do the x's. So what we get is 7 x's is 14. So I know that x is 2. X is always 2. So now I go back to some or any of the equations in the board, say these two equations, and I plug in 2. 3 times 2 is 6. And if I want to get 7, you should be mathematically mature enough to say, 2y minus z is 1. 6 plus 1 is 7. If this is 2, then what's left over to get 0 has to be negative 2. Negative 4y plus 2z must be 0. That creates a problem. This was supposed to be 2, I bet. Sorry. The second equation was supposed to equal 2. The second equation, oh, no. Everything is fine. If this is 2, we just learned that x is 2. To get 0, the rest, and I think I said this, I just didn't write it down. The rest is supposed to be negative 2. I looked at 0 when I wrote down 0 here. But the rest is supposed to be negative 2. And the problem is these two equations are the same. For example, if I divide by negative 2, I get 2y minus z is 1, which is exactly that equation. Now I come and I solve this for z. I bring the z over, and I bring the 1 over. So 2y minus 1 is z. Okay, so we have an open variable z. I can't solve for z. If you have 3 unknowns, but only 2 equations, one of the variables will be what's said to be open. I'm going to say that z is equal to t. So then, I'm going to change my mind on that. Since I have z equals already on the bottom left, I'm going to say y is equal to t. So z is equal to 2t, because y is t, 2t minus 1. 2t minus 1. And here is the parametric equation of the line of intersection of the two planes. X will always be 2. You want to find a number of points of intersection? Plug in different values for t. But plug the same value for t in all 3 equations, get a point, then pick a different value of t, plug it into all 3 equations, get a second point of intersection. Do that as long as you like. And you will get many points of intersection of the 2 planes. And these points will lie on a line. Okay. This one, I'm going to give you a plane, I'm going to give you a line. One to find the point of intersection. Now, if the whiteboard, that is your computer screen or your TV screen, is the plane, and this line is in the plane, then the points of intersection would be everywhere on the line. It would be the equation of the line. However, if this line was right in front of the right in front of your monitor, there would be no point of intersection. Now I wish I knew how to draw well, but if this point is coming right into your TV screen, there's only going to be one point of intersection, right there, right there. So sometimes you'll get a line, sometimes a whole line, sometimes you'll get one point, other times they won't intersect. The line and the plane will not intersect. So here is the equation of our plane. 2x minus 2y plus z is 12. That's the equation of the plane. And here's the equation of a line in parametric form. X is t plus a half. Y is negative t minus 3 halves. And z is 2t minus 1. Well, to find the points of intersection, I would take this new way of writing x and plug it here, and this alternative way of writing y and putting it there, and putting this here. And then you'll get an equation with just t's. And you can solve for t. And if t was 1, then I would come back and say that x is 1 plus a half. Y is negative 1 minus 3 halves, etc. But I'm probably wrong when I said that t is 1. It would be a coincidence if I was right. So let's do that, and we'll be done with this problem. 2 times x minus 2 times y plus z. This is equal to 12. 2t plus 1, 2t plus 1, plus 2t. Negative times a negative is positive. The 2's cancel out. Plus 3. Plus 2t minus 1 is 12. 2t plus 2t is 4t. Plus another 2t is 6t. 1 plus 3 is 4, minus 1 is 3. And this is 12. That must be 15. 15 minus 3 is 12. 15 minus 3 is 12. So 6t is 15. Divide by 6. Okay, 3 goes in here 5 times. 3 goes in here 2 times. Get 5 over 2. 2 times t minus 2 times y plus z. 2t plus 3, 2, 4, 6t plus 3, 15 over 6. Okay, t is 5 halves. So t is 5 halves. And now I can find the points of intersection. X is equal to t plus a half, which is 6 halves, which is 3. Y is equal to negative 5 halves minus 3 halves, which is negative 8 halves, which is negative 4. And z is equal to 2 times 5 halves, which is 5, minus 1. It's 4. 3, negative 4, 4. X, Y, Z. That's where the line and the plane intersect. They intersect at a point. Now, we want to find the distance from given a point and a line, I want to know the distance. If you have a point and a line, you want to find the distance. And Q is the point. 10, -3, -2. And the line is x equals 4t minus 2. Y is always 3. And z is -t plus 1. That's the equation in parametric form of the line. First thing you should find is their direction numbers, which is 4, 0, this is 3 plus 0t, 4, 0, -1. 4, 0, -1. And we turn that into a vector, we'll call it u. 4, 0, -1. Now we want to find the point. Find a point on the line. Well, just pick a value for t. How about we let t equal 0? That gives me -2, 3, 1. -2, 0, 1. So I have a point. I think I said 3. I mean, when t is any value, the y is 3. We will call this point P. So let's find PQ. Arrow says it goes to Q, so Q's the head. You do the head minus the tail. You get 12. -3 minus 3 is -6. -2 minus 1 is -3. And what we want to do now is to find PQ cross U. PQ is it's I, J, K. PQ is 12, -6, -3, and U is 4, 0, -1. And we did hundreds of determinants. This determinant is 6, 0, 24. That is, it's 6 times the vector 104. I factored it out of 6. And now, to find the distance, well, we have all the information we need to find the distance. The distance is PQ cross U, the length of that, divided by the length of U. Now, we don't have everything, but we can easily get it. Now remember, the length of C times the vector is the absolute value C times the length of the vector. The absolute value is 6, times the length of this vector. 1 squared is 1, 4 squared is 16, don't worry about the 0. When I square that and take the square root of that, I get square root of 17. 6 times the square root of 17. So a lot smaller numbers. I don't want to square 6 and 24. Maybe 6 isn't bad, but I sure don't want to square 24. Now U, if I remember correctly, was 4, 0, -1. 4 squared is 16, -1 squared is 1. I get the square root of 17. And that's going to cancel out, so the distance is 6. Which is pretty cool. Now, what if the point was on the line? The point if the point, excuse me, if the point is on the line, then the distance between the point and the line be 0. X is 4t minus 2, y is 3, z is negative t plus 1. The instant I see y equals 3, I'm like, maybe it's on the line. If this were 12, 12 minus 2 is 10. Well, this is 12 when t is 3. When t is 3, get negative 2 for z. All 3 points, all 3 coordinates matched when t was 3. When t is 3, 4 times 3 is 12, minus 2 is 10. When t is 3, 3 is 3. When t is 3, negative 3 plus 1, 2, 1, negative 3 plus 1 is negative 2. That is the point. D is 0. You want to do all your work that I did on the last problem? Take a look at how much work I did. And I think I erased half of it. Here, I did no work. I noticed that y was the same, 3. Like, maybe it's on the line. It's not a bad idea to spend a second or two to see if the answer is obvious. That way, you don't have to do a lot of work. I've had some teachers who are a bit sloppy on making up their exams, because there was one exam where I think half the exam I did no work because I was just able to read off the answer. And the teacher's like, but I wanted you to show me that you knew the work. And I'm like, but you didn't ask me problems that required me to do the work. And we went back and forth, and I had to win in the end because I had the right answers and I didn't cheat. Okay, that finishes this section entitled Lines and Planes in Space. Good luck with it. Study hard.